Okay, so yes, again, we should welcome all of you again to this platform of MEC 451 Thermodynamics. Okay, so like I've told you, we are going to look at tutorials, questions on the past chapters that we have discussed so far. Okay, so this is past year question, December 2018, part B, question 1B. So part A part is just the difference between Otto cycle and diesel cycle. That you can refer to your lecture notes. I would not like to waste my time on that. Okay, so in this question, we are told a 4-cylinder, okay, 4-cylinder, 4-stroke, and 1,500 cc petrol engine, okay, operates on the ideal Otto cycle. And then it has a compression ratio of 8, let me see, yes, compression ratio of 8.7. Now we are told that the engine draws the air at ambient temperature. Okay, so it means air is drawn into the engine at 27 degrees Celsius and atmospheric pressure of 101.325 kilopascal. Now the specific heat rejection, okay, per cycle is 364 kilojoules per kilogram. Now sketch the PV diagram of this cycle, and by using the constant specific heat at room temperature, determine the net work output of this engine. Okay, so this is a typical final exam question. So here, first, let us list down some of the informations that are given in the question. We have been given that it's a 4-cylinder. So given in the question, okay, 4-cylinder. Okay, and 4-stroke. 4-stroke. Okay, so it means, what it means is that if you take something like your MyV car or Produa car, where you have 4 cylinders, and each cylinder is performing 4-stroke. So 4-stroke means that intake stroke, compression stroke, power stroke, and exhaust stroke. So those are the 4 strokes. It's completely different from 4-cylinder. You understand me? So each cylinder is performing 4-stroke. All right. Now, the engine capacity. Engine capacity. So in future, if you want to buy a car, you have to look for this, the engine capacity. Higher engine capacity means higher power. Okay, so here we have 1,500 cc, okay, cubic centimeter. And then we have also told the number of cylinders is 4 already, and the compression ratio. So air fuel ratio is given, and let me see, I have to make a modification on this question. Oh, sorry, yes, so I think it's correct. So we have been given the air fuel ratio stoichiometric, and this thing is given over here. Yes, so compression ratio that is R. I've told you R is nothing, it is equal to V maximum divided by V minimum, and this equals to 8.7. Okay, so now if we are told that now the PV diagram for the cycle, looks like this. Okay, so PV diagram for a cycle is this. Here we have first situation. We have in every Otto cycle, we have isentropic compression from state 1 all the way to state 2. And then we have constant volume heat addition. This is Q in. Okay. And then we have, so this is state 3, isentropic expansion. Okay, up to state 4. This is the power stroke. And then finally we have constant volume heat rejection. So this belongs to Q out. Now, other parameters that is given in the question is such that the temperature at the beginning of the cycle, T1, equals to 27 degrees Celsius. Remember to convert into Kelvin. So this gives us 300. So this gives us 300 Kelvin. So we have 300 Kelvin. Kelvin like this. And then the pressure also P1 is nothing equals to P atmospheric pressure, which equals to 101.325 kPa, kilopascal. Okay, now we are told that the heat is rejected. Let's look at the question again. Yes, so heat is rejected. What is it? So the specific heat rejection per cycle is 36 kilojoules per kilogram. So we have to account for this as well. Okay, so it means that Q out, or Q out equals to 364 kilojoules per kilogram, right? Now, all the data that we required is already settled. Now we have been told to determine the specific work. So find W net. And by definition, W net is nothing. It is Q in minus Q out. Okay. It's Q in minus Q out. And what is our Q in? Q in is given by, that is the change in the properties at state 2. Okay, that's the times the specific heat capacity at that particular portion. Okay, so we need to take note of the information, the equation for Q in and Q out respectively. Okay, so by definition, Q in is nothing equals to CV into bracket T3 minus T2. All right, and then Q out is also equals to CV into bracket T, and that gives us T1 minus T4. Okay, oh sorry, it should be T4 minus T1, very sorry. So T4 minus T1. Yes, so T4 minus T1. So T4 minus T1, like this. Okay, so now we have to determine, do we know CV? CV is given in the question. Okay, CV is the specific heat capacity for air. Even if it is not given, we can look for it in the property table. Okay, it's most commonly used in the, it is available in the property table. So it's not anything which is beyond our reach. Okay, so CV for, if we want to know, CV for air. CV for air is given by 0.718, 0.718. Okay, CV equals to 0.718 kilojoules per kilogram per Kelvin. So that's the value for CV, right? Now, first, let us see what information do we know. We know CV, T1 also is known, but we don't know T2. T2 is not known. Neither do we know T3. So let us find T2. Okay, so find T2. How do we determine T2? T1, state 1 and state 2, they are connected to each other through what? Isentropic compression. Okay, so 1 to 2 is isentropic compression. Okay, so if that is the case, what is the basic equation for isentropic compression? So we have T1 or T2 over T1 equals to V1 divided by V2 raised to the power K minus 1. Okay, so then this gives me R into bracket, raised to the power K minus 1. Okay, be careful. This is coming from this equation, this general equation. P2 divided by P1 equals to V2 divided by V1 raised to the power K equals to T1 divided by T2 raised to the power K divided by K minus 1. So this equation is coming from there. Okay, so now we can determine that T2 by definition equals to T1 into bracket R times K minus 1. Okay, so if you calculate this carefully, we'll have 300 Kelvin, which is K, the value for T1, times R. R is 8.7 raised to the power 1.4 minus 1. Okay, if you calculate this carefully, T2 gives you 712.74 Kelvin. 0.74 Kelvin. Okay, so now we know T2. And with this information now, we can determine also T3. Okay, so how do we determine T3? We know T2 already. We know that Q in is given by, yes, so let's say, you see, even though T3 and T4, state 3 and 4, they are connected through isentropic expansion. Okay, we can use the isentropic expansion equation to determine T3. Okay, so but let us see how it goes. So but first we know this is CV, T what? T3 minus T2. And we also know from isentropic, so let me see over here. So consider, you see, and from state 2 to 3, this is only a heat addition. So constant what? Volume, heat addition. Constant volume heat addition. And 3 to 4, stage 3 to 4 is isentropic expansion. Okay, so now this is given by P4 over P3 equals to V3 over V4 raised to the power K. This equals to T4 divided by T3 raised to the power K divided by K minus 1. Okay, so we can rewrite this equation in this way, that again, T4, so between expression between the volume and then the temperature. So this gives me T4 or T3 divided by T4 equals to V4 divided by V3 raised to the power, we have K minus 1. But be careful over here. You see, what is the definition for compression ratio? We have told that R equals to V1 divided by V2. So, but this again can be expressed in terms of V4, because V1 and V4 are the same. See, V4 divided by what? V3. They are the same. So the compression ratio for both isentropic situations, namely compression and expansion, they are the same. All right. So now,
Sir, I cannot hear you. Open your mic. Hello, sir. Cannot hear you. Okay.
okay. All right. So that gives me okay. So now we have R into bracket K minus 1. So now we are interested in T4. So now T4 means that we have to rearrange this equation. Let me see. Oh, sorry. We are interested in T3. That's what we are interested in. Okay. Okay. So one thing we should know is that T3 is not known, T4 is not known. So we have to go back and then look for T3 first before we can proceed. So how do we determine T3? We can use this equation to determine T3. Okay, because I know Q in, I know CV, I know T2, so I can find T3. You understand? So then Q in is given by 364 kilojoules per kilogram. This equals to 0.718 kilojoules per kilogram, okay, per Kelvin into bracket. Then I'll have T3. So T3 minus T2. So T2 we know already. So that is 712.74 Kelvin. Okay, so if you do this calculation carefully, then T4 becomes, let me see. Oh, so what I did here was wrong. And it is the Q out instead which is given. I'm very, very sorry. So, and this is wrong. So this is wrong solution. I'm very, very sorry for this. So instead, we have Q out equals to CV into bracket T4 minus T1. T4 minus T1. I'm very sorry. So we can determine T4 from this equation. So we have 364. So kilojoules per kilogram equals to 0.718. kilojoules per kilogram per Kelvin. So then we have T4 minus T1. T1 is 300 Kelvin, very solid line. So now, therefore, we'll have T4 gives us, if you calculate this carefully, we have 0806.96 Kelvin. So now we can use this to determine T3, okay, according to this equation. Okay, so T3 will give us T3 equals to T4 times R, okay, minus 1. So then that gives us so 806.96 times 8.7 times 0.4. So then we will have T3 equals to 19.17 Kelvin. Okay, so this is the value for T3, right? So now we know T1, T2, we know T3, we know T4. So now the whole thing becomes very easy. We only need to substitute all the parameters in the equations. So let us determine Q in. So our Q in becomes equals to 0.718 into bracket 1917.17 minus 712.74. Okay, so like this. So eventually Q in equals to 864.78 kilojoules per kilogram. Okay, so therefore we know W net equals to Q in minus Q out. So that gives me 864.78 minus, so T minus Q out, that is 364. Eventually you will have 500.78 kilojoules per kilogram. Okay, so now let's see the next question. Determine the thermal efficiency of this cycle. So how do we determine thermal efficiency? Thermal efficiency by definition is the W net divided by what? Q in. You discover that I'm writing everything in terms of specific quantity because we don't know the mass flow rate of the working fluid. Okay, so that's why we are doing this. So now we know Q in, we know W net, we can find the efficiency. So that gives us 0.78 divided by Q in. So 864.78. So this gives me, if you calculate this carefully, 58%. Now, the next question is to determine the mean effective. Determine the mean effective pressure of this engine. Okay, so let's move to a fresh page. So mean effective pressure, MEP, is nothing. It is the net, W net, divided by V1 minus V2. That is in terms of specific quantities. So this can be expressed in terms of W net divided by V1 1 minus V1 minus V2, and that gives me R. Oh, sorry, V2 minus V1. V2 minus V1. Okay, so what I did, I took V1 out. If I multiply this by V1, I get this. If I multiply this by V1, I get V2. But again, what is V2 divided by V1? V2 divided by V1, V1 equals to 1 over R. Okay, so MEP is nothing, is W net divided by specific volume, 1 minus 1 over R. R is known, we need to determine V1 now. Now, how do we determine V1? So since the working fluid is an ideal gas, so working fluid is ideal gas. Okay, so means we can have PV, P1, V1 equals to MR T1. Okay, but we are interested in specific volume. So I divide it by mass, divide this by mass. So this and this will cancel out. So then V divided by M gives, so our P1, V1 equals to R T1. So V1 therefore equals to R T1 divided by P1. So now let's substitute all the parameters. I'll have 0.2 ideal gas constant for air. What is it? Ideal gas constant for air. So that gives us ideal gas constant for air. So this gives us 0.287. Okay, times T1. T1 is 300 Kelvin, all divided by the pressure, 101.325. So if you calculate this carefully, it gives you 0.8497, okay, meter cube per kilogram. Meter cube per kilogram. So that is it. Okay, so now we will substitute into the MEP. So now finally we will have MEP equals to W net. W net, we have already determined the W net. Okay, so this gives me 500.78 divided by 0.8497, okay, into bracket 1 minus 1 over 8.7. So if you calculate this carefully, this gives you 665.9 kilopascal. Okay, so that is the MEP. Now the last part says we should determine, let's say, the specific fuel consumption, if I'm not mistaken. Yes, specific fuel consumption in kilogram per kilowatt hour. If the engine is running at a stoichiometric ratio. Stoichiometric ratio, this is what we call air fuel ratio. Okay, so air fuel ratio, FR, AFR, is this given by mass of fuel. Okay, it is the mass of the fuel divided by the mass of air, okay, in the cylinder. So we will discuss, it is the mass of the, it can be written in whichever way. So it is mass of the air divided by the mass of the fuel instead. Okay, it could also be written in terms of the flow rate, mass flow rate of the air into the cylinder divided by mass flow rate of the fuel. But in this case, we don't have information about the flow rate. So we will go by the individual masses. Okay. So now, first, let us determine the total mass. You see, it is like this, that when in the cylinder, so if we take this to be the cylinder, okay, so we have air fuel coming inside. So air plus fuel. Okay, so then the total mass of this is given by, let's say, MT. Okay, M total. That's the total mass of the fuel plus the air. So this gives us M A plus M for the fuel. Right? So now we know that the engine, from the engine capacity, so from engine capacity, we are told that the volume V1 equals to, so 15 cc. So this 15 cc is for the whole 4 cylinders. You understand me? But if you are interested in only one cylinder, so we divide by 4. So this total capacity, the 1500 cc, okay, it is for the 4 cylinders. But if you want to calculate only for one cylinder, then we need to divide by 4. You understand me? So now this gives me 375 cc, okay, per cylinder. That's the capacity. It means if you take this cylinder like this, the capacity of the cylinder is given by this. Okay, so that is 375 cubic per centimeters. All right. So if we convert into meter cube, so that gives us V1 equals to times 10 raised to the power minus 6. So that gives us 0.000, okay, 375 meter cube per cylinder. So if you have any question, don't hesitate to ask me. Okay, it's very important. So total mass in cylinder. So the total mass, okay, MT in the cylinder can give us MT equals to absolute volume V1 divided by specific volume V1. All right, so that is it. So now from here, we know the specific volume. Okay, so we have already calculated the specific volume at state 1. So this gives me 0.0000375. Okay, so meter cube divided by specific volume, 0.8497 meter cube per kilogram. Okay, so finally, the total mass now gives me 4.4. Okay, 4.4 times, 4.4133 times 10 raised to the power minus 4 kilogram. So this is the total mass of both air and fuel inside the cylinder is given by this. So we don't know the mass of the fuel separate, mass of air separate. It's not known. Okay. So now, now let us calculate the individual masses. This is coming from air fuel ratio equals to let's see over here. So air fuel ratio gives us, we have mass of air divided by mass of the fuel. Okay, so where again mass of air equals to mass, total mass minus mass of fuel. So if you substitute into the equation, AFR equals to MA divided by MT minus, so sorry, we can substitute by the total mass. So we have, let's see over here, that gives us MA equals to MT minus MF. And then the F fuel ratio gives me, let me correct this. So this gives me F fuel ratio. We have the MT minus MF divided by MF, right? So now this can also be expressed as MT divided by MF minus 1. Okay, so now eventually we will have, if we rearrange the equation, MF mass of fuel equals to MT, okay, divided by F fuel ratio. F fuel ratio we know already, plus 1. Okay, so this gives me 4.4133 10 raised to the power minus 4 divided by 15.7. Okay, so mass of the fuel now eventually gives me 2.811 10 raised to the power minus 5 kilogram. Okay, so now from the equation of the specific fuel consumption, we can have the formula for the specific fuel consumption. Now this gives me mass flow rate. In other words, S, let me change the slide. So specific fuel consumption equals to mass of the fuel divided by the total mass, okay, times W net times 3,600 kilojoules divided by 1 kilowatt hour. Okay, this is for one cylinder, per cylinder. Okay, so per cylinder. Then times and the number of cylinders. Number of cylinders is given by N equals to 4. Okay, so times the number of cylinders. So eventually we will have, and that gives us, yes, so this gives us in kilogram per kilowatt. right? So now I know the values for the total mass. I know that the net work and then the mass of the fuel. I only need to substitute into the main equation. Okay, so then this gives me, I'll have SFC equals 2 into bracket. So 2.811 times 10 raised to the power minus 5 kilogram. That's the mass of the fuel. Okay, divided by 4.4133 times 10 raised to the power minus 4, also kilogram. Okay, times the specific network. Okay, so that is 500.78 kilojoules per kilogram, right? So now times, we have 3600 kilojoules divided by 1 kilowatt hour. Okay, all times 4. So let's see how this thing is going to end up. So eventually we will have 1.832, okay, kilogram per kilowatt hour. Okay, so I think I should, yes, cancel this out. This is not supposed to be there. Yes, this. Okay. Yes, so this is not supposed to, because I've already put in the denominator side already. Okay, so let's move ahead. So here, how does the unit came to this point? You see over here, we have kilogram. We'll cancel kilogram here. And then this kilojoules, which is in the denominator, will cancel this kilojoules out. So then we have kilogram over here. And then we have kilowatt hour. Okay, so times 4. So then that's why we have kilogram per kilowatt hour. So this is the specific fuel consumption for this particular question. Okay, so is there any question so far? I think we have exhausted this question. I'll move on to the next question. Yes, so we have finished with this question. Now let me again add another question. So the next question which we will discuss is related to chapter 4. Okay, so So I'm trying to upload a question, but it's a bit slow. So I have to upload again. 1 minute. So, okay, yes. So then this is the next question, which we need to discuss. Okay. Yes. According to this question, we are told that steam enters a turbine. So we have we have a turbine. Okay. So we have a turbine like this, and this is the exit of the turbine. This is the power outlet. So the W net outlet is this. So the inlet pressure is given P1 equals to 4.5 megapascal, and T1 equals to 600 degrees Celsius. Similarly, P2, okay, so we are told and leaves, so the fluid leaves 50 kilopascal, and T2 138 degrees Celsius. If the power outlet of the output of the turbine is 5.3 megawatt, and the specific heat loss during power generation. So during the power generation, there is Q out, and this Q out specific is a specific heat loss, so it should be small letter. So that gives us 82 kilojoules per kilogram. Now, determine the mass flow rate of the steam flowing through the turbine and the isentropic efficiency of the turbine. Also show the process on a TV diagram with respect to saturation lines. Okay, so here the situation is like this. We are being asked to determine the mass flow rate. Okay, so we want to find the mass flow rate of the working fluid, that's the steam, and the isentropic efficiency. We know by definition that, see, on the, if we consider the either HS diagram or the TS diagram, the isentropic efficiency, so for example, if we have HS diagram, just for illustration, nobody has asked you to draw the HS diagram, just using to illustrate. Okay, so the turbine normally expands. It has a high pressure line and a lower pressure line. And there is expansion, isentropic expansion is this, and this is the actual expansion. Okay, so this point corresponds to, let's say this is state 1, this is state 2A, and this is state 2S. Okay, and the work done by the turbine through this is the actual work, which is given by WA, and this is the isentropic work, and this is WS. Okay, isentropic work. Okay, so by definition, isentropic efficiency of the turbine is given by isentropic efficiency of the turbine equals to W. That gives us the work output for the actual WA divided by WS. And what is the WA divided by W? It is given by the mass flow rate of the steam, H1 minus H2A divided by mass flow rate H1 minus H2S. Okay, so that's the basic definition. But for this particular situation, okay, there is heat loss. Okay, so we need to establish the energy balance for this particular turbine by including the heat loss in the equation. Okay, and if we do that, we will have from energy balance, balance. Okay, so total energy into the control volume system minus total energy outlet of the control volume system should be equal to change in internal energy or change in energy of the system. But again, this is a steady state system. So this equals to 0 for steady state. Steady flow device. Steady state. Okay. So it means the total amount of energy in should be equal to the total amount of energy outlet. So again, now if I draw my turbine for another illustration, this is the inlet, this is the exit, we have the out, W net out is this, and then we have the heat loss. This is Q out. Okay, and the energy inlet, total amount of energy in. Sorry. So this gives me, let me see. From the energy balance, we can write that the energy of the flowing fluid, okay, and the inlet, this is given by E1. And the energy of the flowing fluid and the exit is given by E2. Okay, so now if you consider all this energy, so from here, from this equation, we will have E in should be equal to E out. So the total energy in is E1. That is E1. Okay. This should be equal to the total amount of energy at the outlet. So at the outlet, we have E2 plus W net out plus Q out. Now this Q out needs to be written like this: mass flow rate times Q out. Why did I do this? Because mass flow rate unit is in kilogram per second, and Q is kilojoules per kilogram. See, if you multiply them, this gives you kilojoules per second, which is the same as kilowatt. So because all these W net, E2, E1 are all in kilowatt, you understand? So we have to make sure that this also conforms to that standard. All right? So now, from this equation now, we can define what is E1, what is E2. E1 is the total amount of energy of the flowing fluid. And this is given by M1 into bracket. Okay. So that gives me H1 plus the kinetic energy time and potential energy. So that's the kinetic energy of the fluid plus the potential energy of the fluid at state 1. Okay, so now this should be equal to M2 into bracket H2 plus the kinetic energy terms plus potential energy, and then finally plus W net so plus W net okay, so W net and then plus Q mass flow rate and Q out. All right, so now some terms need to cancel out. You see, we always assume that the change in potential and kinetic energy terms are always equal to 0. So these quantities will be equal to 0, like this. So eventually, we'll be left with mass flow rate M1 H1 equals to M2 H2 plus W net plus M plus the Q out. Okay, so now we can express W net in this form. So that W net is nothing equals to mass flow rate of the fluid times H1 minus H2 plus Q outlet. Okay, so now we are interested in determining the mass flow rate of the working fluid. But first, you see, we know W net already. Q out is also known. We need to find H1 and H2. Okay, so we need to find H1 and H2, then we substitute into the equation, then we can find the mass flow rate. So now, first thing, let us look at state 1. So at state 1, so the working fluid is water. So but we have pressure P1 equals to 4.5 megapascal, and T1 equals to 600 degrees Celsius. Okay, so now one of the basic things we need to do first is to identify the state of the fluid. Is it compressed liquid? Is it superheated? Is it saturated liquid vapor mixture? Okay, so we have to find the saturation temperature at the given pressure. Okay, so T1 from the table, okay, so or T saturation at 4.5 megapascal equals to 257.44 degrees Celsius. So this temperature is less than, T1 is greater than this temperature, T saturation. So it means the fluid is superheated. Okay, so T1 is greater than T saturation at 4.5 megapascal, right? So, which implies what? Super heated. So, superheated fluid. So, if it is superheated, then we have to go to the superheated table. So, from tables A6, from table A6, we will have H1 equals to 3670, okay, 0.9 kilojoules per kilogram. And then we have S1 equals to 7.3127. Okay, so kilojoules per kilogram per Kelvin. Okay, so these are the initial enthalpies and then the entropy at that particular state. Okay, so from here now, let's see, we can determine the entropy at state 2. Okay, so H2 now at state 2, we have P2 equals to 50 kilopascal. T2 equals to 138 degrees Celsius. Okay, so we need to determine, and we have to find the properties at this state. Okay, so but one thing we need to know, you see, if we draw, one thing I need to bring to your mind is like this. If you draw the TV diagram for this cycle, it gives me something like this. So we'll have okay, something like this. So assuming this is state 1, it's in the superheated state. And then this isentropic. So let me draw it clearly. So we have T V diagram. Okay, yes, so this is good. So we have state 1, isentropic expansion, and this is the actual expansion. So this is 2A, and this is 2 what? 2S. And this is state 1. Right? So now, what I want you to know is that we are interested in finding now which of these states belongs to this particular state 2. For this particular question, all the parameters which is given, namely the temperature and then the pressure, is referring to exactly the actual operating condition of the turbine, the exit. It is not state 2S. Okay, so this is the isentropic expansion part, and this is the actual expansion. And all the parameters which is given in the question is related to state 2A. So therefore I'll say maybe this should be 2A, like this. Okay, so now let us see how to determine the enthalpy. So we are interested in determining H2A. So H2A, we have to determine also H2S. H1, we have already determined that. Okay. So now we will have, from this particular state, we can determine whether this state is in the superheated or saturated liquid vapor mixture region by finding, let's say, T saturation at, let's say, 50 kilopascal. Okay, so T saturation at 50 kilopascal. This gives me 81.32 degrees Celsius. So means that T2A is greater than T saturation at 50 kilopascal. So it means state 2A, according to our diagram, is correct. This is superheated. Okay, so this implies superheated fluid. So then we go to the superheated table. Okay, seems to me we need to do interpolation. So from table A6, okay, at 0.05 megapascal, and using interpolation. Using interpolation, we will have a situation like this: T and H 100, 138, 150. Okay, so this gives me 268, 2.4. Then we have H2A. And then this is 278, 0.2. So if you calculate carefully, H2A equals to 138 minus 100 divided by 150 minus 100, okay, times into bracket 27 so we have 27 80.2 minus 2682.4. All right. So now plus. So this gives me plus 2682. Oh, sorry. And this gives me, yes, 2682.4. If you calculate this carefully, so this gives me, let's see, H2A equals to 2756.728 kilojoules per kilogram. Okay, so that is the enthalpy at state 2A. So now we need to determine the, we have to find the enthalpy also at state 2S. Okay, so we need to determine the enthalpy over here also. This will help us to determine the entropy. Sorry, to determine the entropy at state 1 will help us to determine the enthalpy at state 2S, because we know S1 equals to S2S. You understand? So from TV diagram, we'll have P1 or P2 equals to 50 kilopascal, and S2S equals to S1, and this gives me 7.3127 kilojoules per Kelvin. Okay, so now also we have to determine what is state 2S. Okay, so state 2S, what is the state? We have to know that at that particular point, since S2S is greater than SF, okay, but less than SG at 50 kilopascal. So this implies saturated liquid vapor mixture. You understand? So this implies saturated liquid vapor mixture. Okay, so it means that if you find, oh yes, so also this one is at 50 kilopascal. So we have to find SF and SG. Then we will compare with this S2S. So, but we discover that this is greater than SF, but less than SG. So it is saturated liquid vapor mixture. So if that is the case, so therefore we will have, and the value for X, so X2S equals to S2S minus SF divided by SFG. Okay, so this give me from the table 7.3127. Okay, minus 1.0912 divided by 6.5019. Okay, so X2S equals to 0.957. Okay, so that's the value for the quality. So therefore, H2S equals to HF plus X2S times HFG. Also from the property table, so H2S gives us 340.54 plus 0.957, okay, times 2304.7. So H2S 2546.14 kilojoules per kilogram. So that is H2S. You understand? So now, from here, we can determine the mass flow rate. Okay, so let us go back to the main equation. Yes, from this equation, okay, we can conclude. Let me see. Yes, the W net equals to mass flow rate into bracket H1 minus. So now, yes, so now let us rewrite this equation from the energy balance equation. From energy balance, we deduce that W net equals to mass flow rate H1 minus. So now, since we are interested in the mass flow rate, this is going to be H2A minus Q out. Okay. Then we'll have mass flow rate of the steam equals to W net divided by H1 minus H2A minus Q out. Okay. So now, eventually we will have mass flow rate equals to, now W net is given, which is the power 5300 divided by 3670.9 minus 2756.728 minus 82. Okay, so like this. So now, this is in kilojoules per second, and this is kilojoules per kilogram. So kilojoule will cancel kilojoules. So now mass flow rate of the working fluid is 6. Sorry. So M equals to 6.369 kilogram per second. So that's the mass flow rate of the working fluid. Okay, so now, yes, so it's almost approaching 6 p.m. We will finish very soon. Now we need to determine the isentropic efficiency of the turbine. So isentropic efficiency of the turbine So let me see over here. So I'm coming. A minute. So there is a short problem. Let's see. Okay, so I'm having a short problem over here. So, but then I'll try and manage whatever I have at hand. So isentropic efficiency of the turbine, okay, of the turbine can be given by, we have N, so eta equals to W. So we have W net, okay, for A divided by W net, okay, W net for S, okay. So that's the isentropic efficiency. But we can determine W net for A, W net for A, okay, equals to, that's the actual. That gives us the mass flow rate times the H1 minus H2S, sorry. So minus H2A. Oh, sorry. Yes, minus H2 minus H2S. Then minus Q out. So eventually we will have W net. Oh, sorry. This is for S. Very sorry. So W net for S. So I'm having a technical problem with this device that I'm using. So I try to manage it up. We have almost done. So this is W net S. So W net S equals to, if you substitute all the parameters into the equation, you will get 6641, 41.34 kilowatt. 0.34 kilowatt. So now the other W net, let me see over here. And so the work which is given over here, yes. So in this particular situation, this W which is given, this is equivalent to the WA. W net, this is the W net A. W net A is given by this. Okay, that's the actual one. So then the efficiency gives us isentropic efficiency for the turbine gives us we have 5300. So this thing is misbehaving so much today. So this 5300 divided by 6641.34. So the efficiency now gives me 79.8%. Okay, so that is the solution for this particular question. Okay, so I think I would like to stop over here. Okay, if there is any question from any of you, you can let me know now. Okay, so otherwise then we will stop over here. Any questions so far?
No, sir.
Yes, any question?
No.
No, sir.
Okay, so if there's no question, I think inshallah we will stop over here. Our Taskira will be in the next class. Okay, next class also I'll try to solve some 1 or 2 questions. Okay, both in chapter 4 and chapter 5. Okay, so hope to see you in the next class. Thank you very much.
Welcome, Dr. Assalamualaikum.
Thank you, sir.
Thank you, Dr.